What's up, guys? Welcome to another episode of Reason to Doubt, your source for all things skeptical. I'm Jordan, and normally I'd have Jared with me, but today I'm running solo. Macomb has the COVID, so he's not here. And as usually happens when my compatriot isn't here, I'm going to talk about something related to nuclear energy or nuclear radiation. In this case, we're going to be talking about some nonsense that AiG recently threw out there. They claimed that the radioactive carbon in coal proved that the Earth can't possibly be 4 billion years old. Obviously, they're wrong. But before I get into that, as always, we'll be doing our fallacy of the day. Today's fallacy is the ad hominem fallacy. Now, this fallacy is an extremely popular fallacy to get thrown around. It's not one that's actually used very much, but it's used incorrectly all the time. So, what is an ad hominem fallacy? Ad hominem, meaning to the person, is where an argument or an idea is disregarded or said to be false because the person, because of the person making the argument or some feature about them, rather than the audience themselves or the argument itself. So, for example, Fred says that we shouldn't increase the minimum wage, but Fred's an idiot, so he's wrong. Whether or not Fred is an idiot does not, strictly speaking, say anything at all about the quality of his argument. However, this is not an ad hominem fallacy. Fred says that we shouldn't increase the minimum wage. Fred is an idiot, and here is why he's wrong, and then giving reasons. That's not an ad hominem fallacy. Fred being an idiot is not the reason provided for him being wrong. It's just thrown in. So that's what's called an insult. It may be mean or maybe counterproductive, but it's not fallacious. So briefly, if you say Fred is wrong because he's an idiot, that's a fallacy. If you say Fred is wrong and he is also an idiot, that's not an ad hominem fallacy. It might be fallacious in another way. You might be poisoning the well or something like that, but that's just an insult. So if everyone could stop using the term ad hominem for insults, that'd be great. Just tell the other person they're being a dick and move along. So, that out of the way, let's talk about answers in Genesis. So somewhat recently, AiG put out a video. It claims that carbon-14 and things like coals and fossils and diamonds proves the Earth is young. So I'm gonna flip over real quick to our boy Calvin Smith, confidently getting things wrong. So let me pull up the first instance of that. Share my other screen. So this is him starting his intro. If you can't hear, please let me know. I haven't actually run the StreamYard thing before, so we'll see if it works. I think it should work. Let's find out.
A little background on carbon dating. Carbon-14, or radiocarbon, is a radioactive form of carbon that scientists use to date all sorts of things, including coal, diamonds, and fossils. But carbon-14 decays so quickly with a half-life of only 5,730 years, so that none of it is expected to remain in fossils, for example, after about 100,000 years.
So he's right so far. That's correct as far as it goes. That's how long it lasts, and it would go after. Really, the realistic limit is like 60,000 years, or really 50, because there's so little carbon-14 left after that long. But he's going to go on and say some things that are wrong. He does confidently assert that scientists use carbon-14 or radio. Okay. Apparently, I had no sound because I suck at this. Let me try it one more time. Let's try it again. If it doesn't come up with sound, it's not the end of the world, because I can just tell you what he says. All right, let's try this one more time.
Second cry is new radiocarbon was formed directly in the fossils when nearby decaying uranium bombarded traces of nitrogen in the buried fossils. But while carbon-14 does form from such transformation of nitrogen...
Okay, sounds too low. No problem. Let me bump that up. Usually I've got it down to super low because my headphones are pretty sensitive and I don't want to blow out my own eardrums. But for you guys...
Actual calculations demonstrate conclusively this process does not produce the levels of radiocarbon that world-class laboratories have found in fossils, coal, and diamonds.
Okay, So the claim there is some of them you couldn't hear. I'll just summarize for you so you can hear me clearly. Basically, what he's saying is that carbon-14 decays quickly in the geological time frames, having a half-life of 5,730 years. That is too quickly for it to be around for millions of years, such as like the length of coal. However, we find it in coal and fossils and diamonds, and it's not possible to happen unless the Earth is young. Basically, they're saying that the coal had to have been formed with this carbon-14 in it. The counterpoint he was just addressing is the one I'm going to be talking about mostly, which is that carbon-14 can be formed inside the material. So let's talk about how that would happen. Let me back up and talk about radiocarbon dating. What is it and why does it matter? So carbon-14 is a isotope of carbon. An isotope is a fancy name for a different kind of carbon. So all carbon atoms have 6 protons. That's the definition of carbon. The traditional, like a carbon-12 isotope, has 6 neutrons as well. Carbon-14 would have more. Yeah, the two numbers together, you get 14. That's how it works. If you get the more and more neutrons you get into something, the more unstable it's going to get. As you go up the periodic table, it starts being like you need a 1-to-1 ratio of neutrons to protons for stability. Eventually, it goes up. You can think of it as like the protons are all positively charged in a nucleus, and they're packed in together. And if you've ever tried to like push magnets together, they repel each other. Same sort of thing you can kind of conceptualize as happening inside. That's not actually physically what's happening, but it's good enough. And so they want to repel, and the neutrons are kind of like running interference between the protons to let it have stability, to keep the peace between the different protons. Okay. So the way that carbon-14 is formed in our atmosphere is through bombardment of cosmic rays. So the cosmic rays come in, they knock loose neutrons from the nuclei of atoms in the atmosphere, and those neutrons then go and get absorbed by nitrogen, and then they turn into carbon-14. Okay. And that carbon-14 is then breathed in by me and animals and plants or whatever. So you all have carbon-14 in your lungs and in your bodies, and you continue to breathe it in. So you have about the same level of carbon-14 in you as you do in in the atmosphere that you're submerged in. And that'll go on until you die. And then you fall over dead, you stop breathing. And so you stop taking in new carbon. And so that carbon is no longer being replenished, so it'll just decay away. And so we can use the fact that it decays at a predictable rate in order to determine how old something was when it died. Of course, that only works on things that did die. So carbon dating is only useful on biological creatures, things that used to breathe, but now are no longer breathing, or used to take in atmospheric carbon. So with coal, coal is millions of years old. So the things that make up coal, the organic material, did have carbon-14 in it at one point from the atmosphere. Those things died, they got buried, and the carbon decayed away. But now it's millions of years later, so probably none of the carbon-14 from when it was formed is still around. However, he is correct that we do measure carbon-14 in coal today. So what gives? Well, it wouldn't be possible, or it'd be extraordinarily unlikely for any of the original carbon-14 to survive. But if carbon-14 is being produced inside the material, then it would be fine. So the way that actually happens is through the decay of uranium atoms. So when uranium decays, it usually decays through a process called alpha decay. I've actually got a picture here that might help. So let me start this presentation real quick. I did the same presentation on Sal's channel, but I doubt anybody here has seen Sal's channel, so I'm going to cheat and reuse my work over again. So let me share screen 2. All right. So this is the reaction I was talking about that makes carbon-14. You've got the nitrogen here, neutron gets tacked onto it, turns into carbon-14 and releases a proton. Then later that carbon-14 releases an electron and neutrino and turns back into nitrogen. So, uranium can generate neutrons, and here's how that works. So you've got your uranium atom suspended in a bunch of coal, mostly carbon, and usually what will happen is the uranium will spit out an alpha particle, which is a helium nuclei, but every once in a while it will spontaneously fission, and that means it splits into two parts, something like this, boom, and it kicks out two, maybe three neutrons. And so it's going to split into two or more fission fragments. We don't care about the fission fragments for what we're doing. The important part is it spits out the neutrons. So those neutrons are going to bounce their way through that carbon. Carbon doesn't absorb neutrons very readily, so it's not going to absorb much of those neutrons. So it's just going to keep bouncing around. And the neutrons, as they bounce in the carbon, are going to lose energy. This is called thermalizing the neutrons. Thermalizing is just a fancy way of saying slowing down. We could just say slowing down, but then common people would understand it and us, and we wouldn't be able to make so much money. So it slows down the neutrons until eventually it hits something that wants to absorb a neutron. That could be nitrogen. And if it is nitrogen, then that nitrogen will turn into carbon-14 just like that. And eventually the carbon-14 will decay away. So I'll stop this for a second. So that's how it's formed. Now, what's going to happen for a given level of uranium in your sample, you're going to get what's called equilibrium with respect to the amount of carbon-14 you have. So if you imagine the uranium is spitting out neutrons and those are producing carbon-14, that carbon-14 is also decaying away, right? And so as there's more and more carbon-14, the carbon-14 decays faster. I note the half-life stays the same, but because it's exponential, you will get more decays per second if you have more of it. Okay, so that's what I mean when I say faster. So as you build up more carbon, it decays faster, but the amount of carbon being produced is about the same because the amount of uranium decaying is pretty much constant because its half-life is in the billions of years. So we don't need to worry about that. And so because you've got constant production but not constant destruction, eventually you're going to reach a point where the same amount of carbon is decaying as is being produced. And then you'll get to equilibrium. It'll just stay there forever. So what our friend Calvin was saying was that very prestigious and extremely important people have done calculations to show that this is impossible. It can't possibly be done. He does not tell us what those calculations were, and doesn't put it in the comments and doesn't put it anywhere else because, trust him. Like, why would AiG lie, guys? Like, that never happens. AiG has never once said anything that wasn't true. Fortunately for you, I've done the work and I found what I'm pretty sure is the source that they're referring to. It's a source that most creationists are referring to when they're talking about this. They all refer to some vague source off in the distance that they hope you never look at, but I looked at it. So the source was actually Rotta, Rotta. It was published in 2003 in the prestigious journal, the Creation Research Society Quarterly. So it's a creationist research journal. And what he was doing was trying to prove that the amount of, among other things, the amount of uranium in coal is insufficient to produce the amount of carbon-14 we see, which they say if that were the case, then the coal would therefore be young. Okay. So Rotta's paper basically assumes, it uses a assumption called a thin plate assumption. It actually took me a long time to figure out what he was doing, and I'll show you why. So this is Rotta's equation. I could explain what these terms are, but it wouldn't help anyone if I did. These are so when I originally read Rotta's paper, I was struck by, like, it seems like this guy knows what he's talking about because he's using all of the right words, but I'm not sure they're all used in the right way. It was like a very weird way. I'd never seen a equation presented like this. And whether it was intentional to be like hard to follow or unintentional, I don't know. But what he was actually doing was this equation right here, which is much more normal. And so with this equation is describing a beam of neutrons throwing at a thin plate. So what this effect is, it's basically you've got neutrons throwing at a thin plate. They're going to attenuate as they go through the plate. That's a great quote from Potholer, who's one of my favorite skeptics on YouTube. I hope to be like Potholer when I grow up and be as cool as him. I'm not going to say it because I don't want YouTube to come down on me for cursing. I'm not as popular as he is. So, anyways, so this beam of neutrons is going through a plate. Sometimes those neutrons are going to have interactions and they'll scatter away, do something, and you'll have an attenuated beam, a beam with fewer neutrons in it than you started. And what this equation is telling is supposed to, you use this equation to determine how much of the beam is left over. And it's a function of the area of the beam, that's this A. Delta X is the thickness of the plate. N is the number of neutrons, I'm pretty sure. And this is the how effective they are at scattering. So how likely a neutron is. It's a microscopic cross section. It's basically, you can think of it as like the target area of an atom from the viewpoint of a neutron. And this is a very effective formula. It's used all the time in nuclear engineering for thin plates. There's just one teensy tiny problem. A coal seam is not a thin effing plate. The coal seams are really big, you guys. They're like meters thick. Okay. And so it's not the case that the coal is just going to breeze by the neutron's just going to breeze by the coal and it'll be like it was never there. It has a long way to travel to get to the edge of this coal. To give you an idea, the mean free path of a neutron in coal is a few centimeters. The mean free path being how far it's going to travel before it has some kind of interaction. That interaction is probably going to be a scattering interaction. That means that it's going to hit a carbon atom and bounce off somewhere else. It could bounce off in any direction, kind of like a pinball machine. So it's going to be bouncing and bouncing, bouncing all over the place. So it would have to bounce a lot of times to get to the edge of this coal seam. So maybe if you're like at the very edge of the seam, the thin plate assumption might tell you something. But if you're in the middle, it's not going to tell you anything. What it does in practice is it implicitly bakes in a ton of leakage. A ton. He's assuming that the vast and overwhelming majority of your neutrons just aren't going to have any interaction whatsoever, which is complete nonsense. So, what is the real situation? The real situation is, I think, much more likely is that the vast majority of your neutrons are going to be absorbed. You could, because from the perspective of the neutron, this several meter thick coal seam may as well be infinite because it's not many of them are going to leak out, I don't think. And so I ran some calculations to determine how much the production of neutrons in the coal could explain in terms of carbon-14. You have to keep in mind not just how much is going to be absorbed by the nitrogen, but also how much is going to be absorbed by what are called poisons. Neutron poisons are things that absorb neutrons non-productively, so they don't give you anything in return. For a good example of that in coal is boron, which is also used in nuclear power plants because it absorbs neutrons like crazy. And so when a neutron hits this boron, it gets absorbed, it destroys the boron, but no more neutrons are produced, so it kind of shuts down that life cycle. And so I did some math because that's what you do when you're trying to actually do science. So I will show this math. I'll put all this in the video description later. Yeah, actually, I think that is probably actually that's actually a really good point. The mutation rate as a fixation rate for those who aren't like hip deep in creationist nonsense. It's very popular argument in creationists nowadays. Jeanson, the very extremely cool guy from Harvard, has made this mistake. Basically, he uses the mutation rate going from father to son and says, okay, that mutation rate, that's the same. You can use that rate as the rate in which genes become fixed in a population. Because apparently, when I passed autism on to my son, every person in the freaking globe got autism. It's stupid, but it's one of those things that you only realize is stupid if you know a little bit about what you're talking about. Somebody who had no idea what they were talking about looking at that equation would have, I mean, would look good to anybody who has no understanding of nuclear engineering. But fortunately, that's why I'm here, to tell you it doesn't in fact look good. So let me share this just so you can follow along my calculations. You probably can't see that. Okay, so I've got some assumptions like you'd have in any good stuff. I already talked about those. Basically, no neutrons are going to leak. Neutrons, there's 3 fates that a neutron could have in this coal. It's either going to leak, which there's a ton of coal, so I don't think much is going to leak. It's going to be absorbed by something, whether that's nitrogen or boron or whatever. It's going to be absorbed by something, or it can decay. A neutron on its own, that's just hanging out, it's not very happy with itself, doesn't like to be a neutron for very long. So in about 10-ish minutes, it'll decay into a proton. But because the neutrons are moving extremely fast, the slow neutrons that I talked about, the thermalized ones, those are moving only at about 2,200 meters per second. And that's the slow ones. The ones that are coming straight out of fission are moving at an appreciable fraction of the speed of light. So they're not going to hang around for 10 minutes in this cold seam. So we don't have to worry about those either. Other assumptions, the amount of nitrogen and carbon and stuff doesn't change. There's not much production going on, so we don't have to worry about it like eating through all of the available nitrogen in the coal. There's some constants and some cool numbers. Basically, the way you do this is you figure out first how many atoms of coal you have in your sample. Because we're assuming it's an infinite mass, the actual number of atoms doesn't matter so much. If you were going to do a discrete mass, the actual number of atoms would matter a lot more. What matters is the proportions of those atoms. So how many of them are carbon, how many of them are uranium, how many of them are boron, and so on. Okay. So with that number, we can figure out the activity of your uranium. Okay. So in any unit area of your coal, you're going to have so many uranium atoms. So I took this number and then I found percentages for like how much, what's the trace amount of uranium, what's the trace amount of boron, and so on in your coal. And from that, I got a number of uranium atoms. You multiply that by the decay. I'm not going to, you know what? I'm not going to go through every single step of this because nobody cares about this but me. You do some magic math and you get to an activity number. That's how many are decaying. This BQ, that means becquerels. So you're doing 6.75 times 10 to the third becquerels decays per second. So neutrons are being spit out. This is how many neutrons you're producing per second. That's what all that was for. That's how many neutrons we have to work with. Now, because we're assuming that no neutrons are lost, that means that all of those neutrons, that 0.92 neutrons per second, those are all being absorbed, right? And so I first did a calculation assuming that there were no poisons just because I was lazy. And if you do that, you can get an apparent C-14 age. So if you took like the equilibrium amount of C-14 and converted it into percent of modern carbon, which is not actually accurate at all because this carbon did not come from the atmosphere. So it has absolutely no bearing whatsoever with radiocarbon dating. Do not radiocarbon date coal because you won't get good results. But this is what you would get if you like send it to a lab, didn't tell them what it was coal or whatever, and they just tested it and whatever. This is the number they'd come up with. So 43,000 years or so. Definitely not zero, but a small trace amount. But there are neutron poisons. There's a good amount of boron in the coal, and also sulfur is a decent neutron poison. You can tell by their cross section. The unit Barnes is 10 to the negative 24th centimeters squared. That unit doesn't matter. Bigger means it absorbs more. That's all you need to know. So basically, the way I did this was I took a sphere of coal and then I took out all of the carbon atoms. So you only had boron atoms, and I figured out how many boron atoms would do absorptions. And I did the same thing for sulfur and the same thing for nitrogen. And then I compared the two. I compared the three, rather, in ratios. And it turns out that about 32%, about a third of your neutrons will be absorbed by nitrogen. So you do all of that fancy math and boom, you get to an age of 51,000 years. So what does this actually mean? It means that for average amounts of boron and average amounts of uranium in your average coal seam, it will, if you sent it to a lab, you would get an apparent age of 51,000 years. So it is simply not the case, as AiG claims, that the presence of carbon-14 in uranium or in fossils or in diamonds. I haven't seen any actual fossil stuff, but I've seen the bit they talk about in diamonds and coal. It's simply not the case that that necessarily means that all of physics is wrong and we need to upend everything you learned, because there's other mechanisms that these things could show up with. Now, this is only one of many different mechanisms that you can have. It's the one I'm most familiar with because that's to do with radiation, so it's the coolest, obviously. But there are other ones. Simple contamination, not just of the sample at the time because it's full of groundwater and stuff, but also in the lab. It's actually kind of ironic to me. If you watch the video or any video with creationists talking about this, they will go to great lengths to talk about how much work the scientists do into making their samples clean and purified and like getting all the contamination out, which is true. But it's funny that the same people who want to say that these scientists are incompetent, are lying to you, and have no idea what they're doing, we can trust that they're being good with the samples. I don't know how we can trust them. I guess it's when they agree with them, it's okay. But those scientists will tell you that no system of purification is going to possibly be 100% accurate. So even when they put in a blank to like calibrate the system, this is another thing that Calvin says and is lying about. He says that we know that there's no contamination because when they put a blank in the machine, a blank meaning a hunk of graphite or something with like no carbon-14 in it, supposedly, it comes up with a reading of 0. That's bullshit. It doesn't come up with a reading of 0. It comes up with a non-zero, a very low reading, but a non-zero reading. They use that to calibrate how much background radiation and how much like background C-14 there is, and then they just take that off of their future measurements. So like if you have this much carbon-14, that that's just noise. Then when you get a sample of this much, they just reduce it by that much, if it makes sense. So bottom line, if you hear any creationists talk about carbon and coal, you can shoot them to this video and the math I did. And this is not that complicated of math, to be honest. Like, I'm just an undergraduate engineer. I'm not a physicist or anything. Like, people like Andrew Snelling who have PhDs like from real universities, they should know better. This kind of stuff should not slip by them. And the fact that it doesn't do a lot to shouldn't do a lot for anybody to imbue with confidence that they're talking that they're being rigorous in any of their other work. Because if something as simple as this is getting by them, then what else is getting by them? That's the way I look at it. So that's carbon-14 and coal. We're only at about half an hour. So does anybody, I can talk about other stuff. I can talk about other things that Answers in Genesis is wrong with, or we can just end now because I don't want to take everybody's time. Yeah, so in doing this, some other bones I like to pick with Answers in Genesis, since Jared's not here to reel me in. So if you leave me alone, I'm going to talk about radiation. Another thing that grinds my gears is when they talk about radiocarbon dating, when they talk about radiometric dating, and they talk about like inherited argon is one of their favorite things. So they'll say, how can you trust a radiometric dating method when it doesn't work on rocks of known age? And the one they always go to is Mount St. Helens. They'll say, look, Mount St. Helens erupted in the 1980s. We know exactly when it happened. And then we went back 10 years later and we took a sample and we sent it to a lab. And you know what? The lab said it was 100 million years old. And if it's that wrong when we know how old the rock is, imagine how wrong it is when we don't know how old it is. The reason that is bullshit is because the source of error, and they'll often even say this, they'll say that the reason it's wrong is because of inherited argon. So what does that mean? The argon method or the potassium argon method, they're related, uses the fact that potassium, which is present in lava flows, decays into argon, which is a gas. Now, most of that gas is going to have escaped from the lava before it crystallizes because it's a gas. So, it's not going to want to hang around. The lava is flowing, it cools down, it crystallizes. Now it traps everything inside it. The idea is, the kind of naive assumption underlying it is that all of that argon would have outgassed, it'd all be gone. In fact, that doesn't happen because the real world's messy. You're going to have some amount of inherited argon, some argon that didn't quite escape and is trapped in. The reason this doesn't matter when you use an appropriate method is because argon dating is best used for like old samples, things that are like millions of years old. So if you're sampling something that's a billion years old and you have an error of a million years, that's not a big deal, right? If you sample something that's 10 years old and you have an error of a million years, well, that's a huge deal, right? The problem is not enough argon has built up from decay to outweigh the static amount of argon that is inherited. That inherited amount stays the same. So it's the same number of years of argon, if you like. That doesn't increase over time. So the older your sample is, the less and less that inherited argon matters, to the point where if you get sufficiently old, you can completely ignore it. The way to think about this is it's kind of like if you used a truck scale and you sprinkled like a tiny bit of salt on it and then bitched that it didn't give you an accurate measurement. Well, no shit, it didn't give you an accurate measurement. You're using the wrong size scale for the thing you're using. And that's what's happening there with Mount St. Helens. It's in a perfect world, if there were no sources of error and scientists could count every single atom without any kind of noise, then yeah, you could use the method there. But we don't live in that perfect world. So as usual, just more creationist nonsense. Well, I've rattled on enough. I don't want to take everybody's time, but I appreciate the folks who dropped in. If you did enjoy it, leave us a like, comment, subscribe, the whole YouTube thing, share with everybody. And hopefully Jared will rub some Suck It Up onto his lungs and be better. And we'll be back together next time. So till then, thanks for coming. And remember, you've always got reason to doubt.